One of the things that I wanted to establish was the connection between a state function, U, S, V, and N, and partial derivatives of this quantity, partial U, for example, partial S was the temperature, and this would be at fixed V and N. So the idea of taking partial derivatives of state functions is a fundamental idea that underlines everything we're going to do for the next however many weeks, 15 weeks. Partial V is minus the pressure. This is at fixed S and N. It's minus the pressure. That's just a convention, whether or not it just kind of makes sense in terms of the way we think of pressure and what happens when we compress something. And this is partial S.
We're using same link.
Huh?
We're using same Zoom link. The same Zoom link.
It's the same Zoom link every time. Can you not open it? Or maybe he doesn't know. You're here. I see you. I see you right here.
No, that's me.
That's who?
It's Rita. I just registered for the class yesterday.
Can I see you so I know who you are?
Right now, yeah, in a minute.
Okay. How did you get the Zoom link? You went to Canvas and got it, right?
Yes, I did.
Okay. Are you a physics student?
No, I'm a chemical engineering student.
My goodness, I'm overwhelmed with chemical engineering students. Who do you work for? Do you work for Kalu as well?
Yes, I do.
Okay. Are you doing density functional theory?
Yes.
Okay. I didn't even read the name. I just saw C and I thought it was him and I went on from there. All right. That's fine. Real quick, just because I didn't realize I would have a new student this late, it was not that late into the class. I'm going to go ahead. There's Mr. Bosa. I'm going to go ahead and tell you real quick. I'm Dr. Encinosa. My office hours are Monday, Wednesday, Friday, 11 through noon in room 110 across the hall. I don't know if you've ever been here. And then Tuesday, Thursday is for you guys Zoom because I know some of you have to go back and you can't hang around. So if you don't want to fight parking, don't want to wait around, class ends at 12:15 and you have to get back to your responsibility. Some of you are actually paid by the hour, I'm guessing. So you have to get back. You can get on Zoom and the same Zoom link you're using right now. Got you now. Okay. I just read the chi and I thought it was you. All right. So real quick, I will actually go ahead and post these notes because you are essentially one class behind. And the first thing you have to do is mute me. Actually, you have to mute your computer. So I get feedback. Testing, 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 testing. That's you. No, that's you. Hello?
Hello?
Pronounce your last name for me.
Akunne.
Mr. Kune,
Yeah.
you have to mute your computer. So I get feedback from you. Everybody has to mute their computer or I get this feedback. You saw how to do it last time, right?
Yeah.
Mute, mute. Okay, we're not doing well here. You're not even on yet. So it's not you. I don't think you muted your computer. I think you muted you've muted you, but you haven't muted everything. Testing, testing. Okay. Miss Acuna, as befits a young woman, figured this out much more quickly than a young man. So maybe she didn't. Testing, testing. No, she did. She did. Yeah. Do you know these guys?
Yes, I do.
Okay, how unfortunate. Oh, there you are. Okay.
Yeah.
All right. So we are dealing, just a real quick thing to catch you up. I need to know a little bit about you, okay?
Okay, so my name is Rita Akunne. I am a third year PhD student chemical engineering, and I work with Dr. Kalu. Yeah, I'm Nigerian, and yeah, that's it.
All right, so what was your undergraduate degree in?
Chemical engineering.
Chemical engineering. Have you had a thermodynamics class?
Yes.
Have you had a chemical physics, what's the physical chemistry class?
No.
If I say particle in a box, Schrodinger equation, does that mean anything to you?
Yeah. I mean, yeah.
Kind
I
of.
kind of, yeah, because we did that in the thermodynamics
Okay,
class.
so we're going
So,
to, because when I hear yes, of course, I understand that fully. If that's one, if I hear kind of, we're going to go through it again and keep the course as self-contained as possible. So don't panic.
Thank you.
I try to teach the course from first principles, so I've got to continue now. Do you know what? Have you heard the words entropy is a function of energy, volume, and
Yeah, yeah, I'm very familiar with that.
okay, so you also know that entropy and these two are invertible, and you can take total differentials to get thermodynamic quantities like temperature, pressure, and chemical potential, correct?
Yes, yes, I do. Yeah.
You're good there. So you also know the difference between extensive variables and intensive variables.
Yes.
Okay, extensive, intensive. Okay. And we learned last time as an in-class exercise, you can define something called the free energy that accounts for entropy in a little bit more familiar way. And as a chemical engineer person, this might be, you guys use Gibbs enthalpy too? Or you guys, what's the one you guys use mostly?
Helmut's.
Helmholtz free
Yeah.
energy?
Yeah.
Okay, that's also all contained in here as well. We'll get to that a little bit later when it comes up in class. Do you know what the Boltzmann factor is?
Yes.
Okay.
That's
I have to then. I'm glad you're here, but why are you taking the course if you know all this stuff already?
um um I wouldn't say we know everything.
It's all fun and games until somebody asks you tough questions.
Yeah.
Okay. Well, if anything, at least it'll be a refresher for you.
Yes.
Okay. All right. So last time we talked about we did an in-class exercise to show how defining the free energy as U minus temperature times the entropy, taking total differentials. I'm going to do that for you guys are out of luck. I'm doing that from her from scratch. Okay. I'm sorry. You're just going to have to wait. It's an important example. I want to do it. So I'm going to do this for you because this is a really important example of everything I just talked about for all intents and purposes. Because I think it's kind of like I said, all fun and games until somebody actually makes you do it. No, I don't know how to do that. Cut that. Because we use this trick repeatedly in this class. Almost. Got it. So mm, we started out with U, the energy function of S, V, and N, and we took partial derivatives. In fact, that's what I was talking about before I noticed your name. Then we talked about partial derivatives, like for example, partial U, partial S at fixed V and N. And if you took the class, you know that this is the temperature. And I'm using capital T later on. We're using tau. Um, okay. And this is just the machinery of how we do this. This is called a Legendre transformation. It's the first one you generally encounter in a course like this. You said you were on Canvas?
Yes.
Okay, so the Zoom link you already have. I do have the YouTube, don't I?
Let
MRE
me see.
underscore physvids. That's where I post all our lectures. You can go back and watch the lectures again, again, and again. Okay.
Okay.
By that I mean 0 times for most of my students. But you can go watch it the 0 times most of my students actually do it.
Okay.
So if I take a total differential, and this is the philosophy of a lot of what we do in here, we're taking total differentials and looking at partial derivatives. If I take df, this is du minus t ds minus dts. And we know that du in this situation is du, let's just write it out. It is equal to TDS minus PDV plus mu dn. And then I have minus TDS minus I'm going to write this as SDT just to make it a little more transparent because I don't like where that D is. SDT. It's the same quantity, just cleaned up. We see that these two quantities cancel, and this is at the heart of this Legendre transformation business. This also happens. Only one of you have the context for this. As I spoke last time, when you do canonical transformations, you go from one to another, you see this cancellation happen all the time. So dF then will be equal to SDT minus PdV. And if I include the mu dN, it would be here. And I don't have that in the notes, but that's okay. So one of the things you have when you take a differential, and this is what I did in the first part of the class last time, if you take the differential of an arbitrary function, and I'm not even going to use XYZ, I'm going to use UVW, has nothing to do with thermodynamics. I emphasized last time, this is a statement about mathematics. It's not, has nothing to do with physics, and I emphasized last time that it is our job as in physicists and chemical engineers, a little bit less so, to start making connections between these things. So I see that if I have a dt and I have a dv and I have a dn, whatever's in front of this, according to this philosophy, matches up in a one-to-one way. That's the whole utility of thermodynamics. So df for us is partial f partial t dt plus this must be partial f partial v dv plus partial f partial n dn. And in each case, I'm taking the dt, and that's my differentiation variable. dv, that's my differentiation variable. dn, that's my differentiation variable. So I identify s with partial f partial t at fixed v and n, because when you take a partial, that's what that means. We say that to you in Calculus 3 again, again, and again, and it only hits home when you run into a problem. We also identify P as minus partial F partial V at fixed T and N and mu as partial F. And this is more or less where we got before I started to move. I just wanted to make sure you saw this, because if this is not something that you immediately look at and go, I'm good, then it's a good time for you to go back and write this stuff down on a what, you might ask? On a 4x6 card. Write them down, put a piece of tape in the back, and slap them on your refrigerator door. So every time you go to get a beverage, you look at them and you're reminded of these very important and critical points at fixed T and V. All right, good. So we did that, and I mentioned that because of the nature of this the subject, if you were to ask me, can you say your last name again for me? Akune?
Yes,
Akune.
yes.
Akune. If you were asking for Westerners, it's hard to get the accent in the right place. Akune.
Kunne.
Akune.
Kunne.
Akune. I'm saying exactly that. In my ears, I'm saying exactly Akune. Akune. I'm sorry if I'm messing it up.
No, it's fine.
It's Akune. Miss A. Just gonna use A.
Okay, that's fine.
If someone asked me what this class is about, it's about connecting quantum mechanics to thermodynamics. All right. The intermediate steps that you need to connect quantum mechanics to thermodynamics is in these state functions, U, F, Gibbs maybe, things like that. So the state functions are the bridge because they are so robust. Robust means they hold up. They are almost universally true that if you have the free energy, you can take derivatives and get the appropriate quantity in thermodynamics. All right, so speaking of thermodynamics, we started talking about the laws of thermodynamics. If you have the notes in front of you, can you access the notes, Ms. A?
Not, let me see. I
Are you on
haven't,
Canvas?
yeah, I'm on Canvas. Let
Is
me
there a
go to-
module there? There should be a module 1 that says review mat, rev mat, or something like that.
Okay, yes.
You can open that, and that's the set of notes. Are you in an office or are you at home?
I'm at home.
If you have a printer, feel free to print them out. But if not, you can read them off the screen too. Okay.
Okay.
So this is the 0th law of thermodynamics. and I had a discussion that nobody was interested in but me when I, but the discussion was this. So there exists a scalar quantity such that if two systems A and B are placed in contact, they reach an equilibrium value, and that equilibrium value is the temperature. And I sat there and I spent a good 2 minutes talking about time scales. And what I meant by that is when you put a bag of water or a cup of water, maybe take a plastic bag, take a sealed plastic bag of water at 35 degrees Celsius, 35 degrees Fahrenheit. I don't know what that is, Celsius. You guys think it in Fahrenheit or Celsius? You guys work at Celsius. Okay, so take it at 5 degrees Celsius, so it's cold. And you put it in 30 degrees Celsius, which is warm. They come to an equilibrium. And you know that this guy doesn't change if it's a big tank of 30 degrees Celsius water and you drop the little itty bitty ice, a little bit of cold water in there, this temperature doesn't change much. This temperature changes an awful lot. That's an idea I'm introducing now of a reservoir, that this big thing comes along and exchanges energy. So that happens pretty quickly. However, the thermodynamics, the question, the conversation I was having essentially with myself, because these guys think, why is he talking about this for 3 minutes when I understand it immediately? Is you have to be aware of the time scale. There's a very famous, you guys know who Richard Feynman is? Have you ever heard the name Richard Feynman? You've heard Feynman?
Yeah.
Where did you hear Feynman? In
It
chemical engineering.
It was actually a movie.
Oppenheimer.
Yeah.
Oppenheimer. So Richard Feynman was the youngest head of a division, and he was just a Nobel Prize winning physicist. And he says, when we do thermodynamics, you should bear in mind always, I'm over talking this again. You guys wish I would shut up. I know that. But when you talk about thermodynamics, you should also be aware. For example, evaporation is a thermodynamic process. And what happens in evaporation is you have a liquid, and eventually, if you put a liquid in an environment that's warmer, this right up here collides, the surface or somewhere collides with the molecules on the outside, and occasionally they pick up enough energy to leave, or they're just through thermal fluctuations, they work their way out, get over, there's surface tension. You have to overcome surface tension, which is why things don't evaporate immediately. However, if I were to ask you to take a piece of metal in outer space and I were to wait for it to evaporate, you'd be there. Mercury, for example, you guys know mercury is a liquid in thermometer. Like, I don't know if they don't do it anymore. It's too dangerous to put mercury in thermometers, I don't think. But in the old days, you'd play with mercury, and it was this quicksilver fluid. It would take a very, very long time for mercury to evaporate. So everything's on a scale. I'll stop talking about that now. I just think it's such a fascinating idea that thermodynamics depends on this scale of the problem. Okay, I've done this 4 times now. Cut. Eureka. And action. All right, so that is the 0th law. What about the first law? The first law says this: it's a statement of conservation of energy. A small amount of energy change in a system is equal to the heat added to the system plus the work done on or by the system. Note that dq can be TdS. We also have to know that dW greater than 0, work is done on the system. That's the convention. Here's where the engineering culture is a little bit different than the physics culture, because when I heard you were in this class, I knew this already, but I went and got an old Shams outline. You know what a Shams outline is? On engineering thermodynamics. For you guys, oftentimes, I don't know if this is still true, but work greater than 0 is work done on the system.
Can you say that again?
When the work is greater than 0 or before that?
What greater than 0?
If the work is greater than 0, I'm doing work on the system.
Oh.
And the easy way to remember that, if this is dW greater than 0, then the energy, which is on that side, increases. That's why physicists like it.
Maybe it's our
It's a different convention. Yeah.
wrong idea.
Yeah. Well, you're gonna have to get rid of that. You're in a physics class now, buddy. You either do it my way or the highway. If you ever heard that phrase Americans use all the way, my way or the highway. No, well, yeah, that's a good, it's a perfectly reasonable convention because you're dealing with environments,
Yeah.
right? The thing about engineers is the environment is finite.
Yeah.
Your problem is so hard compared to ours. Because how do we teach this class? How do I teach this class? How does every statistical mechanics class of this type be taught? The reservoir is infinite. It's all fun and games now. Anybody can do it. When the reservoir is finite and you have to worry about the reservoir getting ruined in the process, for me, it's infinite. You can't ruin it. For you, oh my God, I'm running out of energy. I'm doing all this work from the environment. I need another source of energy to keep the machine running. Yeah. So it's work done on the system. Obviously, D for us, less than zero, work done by the system, and that decreases the energy. Okay. The classic example of, I told you guys I would not make you strain to read my writing. I'm capable, just not disciplined enough. All right. Would you fill her? I'll email her separately, actually, now that I think about it, about the textbook information on that. Okay, good. The classic example of a system doing work is a gas pushing against a piston. And I'm going to ask this question now instead of waiting. So we know the work done. If I push this thing down to here, call that delta X, the work done is F dx. And I know that the force is pressure times area in this simplified system times dx. And in this case, we do positive work on that system, right? So this is dW is equal to 0. You'll notice if this is also PdV minus PdV. I put a, just to emphasize, this is a small point that people don't emphasize, but this should be plus here. If I can fix that. Because actually V is smaller, right? So dV is negative. But if you think of it this way, here's the reason fundamentally you have a minus P when you do partial U, because in this case, this is, forget what the note says for a minute. I have a better way to explain it in front of you right now. You always see this thing that you always wonder, you always wonder, again, partial U. When I get excited, when I get excited about something, this is always like panic and, I hit all kinds of weird buttons. Partial U, partial V is equal to negative P. Why the heck would you need negative P for this process in a simple way? Because this is definitely, when you do work on the system like this, you definitely increase the energy, correct? You definitely increase it because you're doing work done on the system. But if you look at PdV, in this case, dV is less than 0. That's negative, isn't it? And P then is positive. If you kept P positive, then you would have a negative amount of work done. So you define P to have a negative value. So negative P times a dV less than 0 is now a positive number. And I'm going to ask all three of you a question. Are we ready for this question? I ask it later in the
Yes.
class, but I'm ready now. I don't have chemical engineer. I don't have engineering students that often. This is fun for me. He's probably heard it. Victor's probably heard this from the students who are in physics. All right. So you've taken general physics sequence, and there's no embarrassment in not knowing this answer. Okay.
Okay.
You've taken general physics 1, general physics 2. You've taken courses in thermodynamics. You've taken a course in statistical mechanics, chemical physics, perhaps. You've taken a course in transport. Okay. I'm assuming both of you, third year PhD students, you guys know your stuff, right? So here's this piston, and I compress it, correct?
Yeah.
What happens to the temperature? That's not a trick question. We all know this, right? You compress it, do work on the piston. What's the temperature do? It increases.
Increases.
It increases. All right. Why? Explain it as if you were explain it to a 12-year-old. Why does the temperature get higher? Why does the temperature increase?
The way I would see it is that the particles become there's like a higher interaction between the particles and it generates
It's true for an
heat.
ideal. That's okay, and one by one, I'm gonna tell you why that's not the answer. You ready?
Okay.
It's true even for particles that barely interact at all. Like even for argon, even for neon, what are those gases called? Noble gases. Still works. It's not part of it, it's it even works for the most ideal of ideal gases. It's not because the particles interact with each other. Keep going. Anybody else?
That would have been the answer.
Yeah, okay.
That the whole movie.
So here's okay. So here is but we agree there's particles of gas in there.
Yeah.
We agree. Okay. So same thing, people in my undergraduate physics classes, I've had graduate students, okay? Can't give me the answer immediately. And there's no problem with this. This is a question of teaching you something, the way to think about these questions, as opposed to you not being smart. You're very smart, both of you, obviously. That's not it. What it is also I'm excellent at this. That's another thing. So I will teach you this very carefully. So a 12-year-old sitting here, and what the 12-year-old or my 21-year-old students will tell me, well, the volume is smaller. Okay. Suppose I take an aquarium full of gas this big and I put a cover and it's a temperature 20 Celsius. I drop a pane, a glass sheet in between them. Does the temperature go up? It does not. Here and here. Clearly, the piston moving has something to do with it. Agreed? If the piston's not moving, what happens to the temperature? Nothing. Now I'm going to go back to what Ms. A said. There's particles in there, right? What else do they say? Oh, because the particles are closer together. It's closer together. Some students will go, well, because they go faster. I say, yes, that's the definition. You're not asking, you're giving me what it means to be hotter. You're not telling me why it's hotter. I'm asking why, right? Okay, so in here is the piston, right? What's happening in there with these particles? They're all moving around like this, correct? 1/6 of them, how many dimensions of space are there? 3. If it's random. 1/6 of them are going this way. 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 They just hit the containers and bounce around, right? 1/6 of them are going down. However, what's the other 1/6 of them are doing? They're going up. So you guys play cricket?
Yeah, yeah.
You play cricket? You ever play cricket? Baseball? Something like that?
Okay, yeah.
Okay. So 1/6 of them are doing what? Heading up. If you're not moving the piston, they go down. However, if you're going up and the piston's coming down, they turn around faster because you're doing work on them. You're colliding with it with a speed v coming down. And this is big and this is small and it recoils faster than when it comes in. In American baseball, we have something called exit velocity, where how fast the ball is going out.
Can you come again? Excess. What did you say? What do you call the velocity?
Exit, leaving,
Exit.
leaving,
Okay.
leaving velocity. So the pitcher throws it 90 miles an hour, a batter hits it, and it goes out 102 miles an hour. It goes out faster because he's using his body. He's doing work on the ball with the bat, with a force through a small distance. It's an impulse, basically. I don't know if you remember, it's an impulse. Big force over short time, changes the momentum. V final bigger than V initial.
Okay.
FDT is F delta P. MV final minus. We didn't have one in that qualifier though. We should have put one like that on there. So it goes out faster, and that's what's happening here. It goes out faster, and that's hotter. Hotter is faster. So the 1/6 that are going up hit the piston who's coming down. Why does it cool? Why does it cool when you pick the piston up? Here's why it cools. If I throw something at you, a cricket ball, that's why I cricket, because I don't know if you knew anything about baseball. It's the same thing. Hit it with a cricket bat, out goes the cricket ball. If I throw a baseball at you, you don't, at high speed, you don't hold your hands like this. You do this, you give. You're taking some of the velocity, you're shedding some of the velocity. So when you're coming up and the piston's already going up, you're giving some of that to the piston and it goes up and gas expands and it cools down because now these molecules have given up kinetic energy, which means lower speed, and that's why. And this is a good example of thinking about the problem at the atomic scale, molecular scale. Okay, yeah.
So at that point, what happens to the particles of gases that collide with each other?
It's very much like what happens this is a good question. It's a really good question. It depends on the nature of, again, in physics, we're doing ideal situations, right? The ideal gas law is really, and I have you'll see here in a minute, I have all the suppositions are the assumptions we make for the ideal gas law. If the molecules collide fast enough to excite internal degrees of freedom, it's a much more complicated process. Because then, if they excite internal degrees of freedom and emit radiation, for example, then the energy is lower no matter what. But for us, we almost always deal with the ideal gases, spherical particles. When they interact like pool. You play pool?
Yeah.
Pool, billiards, snooker, if you have the English tradition. I don't know which. Yeah, just two metal balls colliding. They just go off and don't. They exchange energy, but the average kinetic energy of all of them are the same. That hasn't changed. When they collide, nothing changes. Because at the fundamental level of atomic physics or molecular physics, the collisions, if they don't excite internal modes, are elastic. And I'm going to follow, you asked me a good question. I'm going to follow up on that. Okay. So then you start to ask, what kind of energies does it typically take? What kind of energies does it typically take in order to get excitations, right? In the case of a molecule, there's these degrees of freedom. 1, 2, 3, right? For a spherical molecule, that's all there is. And if you remember general physics, this is where the kT comes from. 1/2 kT, 2/2 kT, 3/2. I don't know if I did that right. 1/2 kT, 2/2 kT, 3/2 kT. The average energy is 3/2 kT, right? However, if it's a molecule like an argon that's a sphere, that's all you got. To excite anything in there it takes a tremendous amount of energy. All right, we're going to have a deep discussion about scales because that's what a lot of this class is about, scales of energy and excitations. If the things like nitrogen, N2, right? N2, 1/2 kT more, 1/2 kT again. That's 5/2 kT, right? So for a case like N2, you now have the opportunity to excite something because it can do this. That's much lower in energy. Okay. But even if you do that and excite this, the vibratory mode, the oscillator, okay, you can excite this, you can excite this, and you can excite this. So you got now 3 kT as opposed to 3/2. Then you have to start asking what are the scales of the energies involved. I'm going to tell you this because I'm just riffing on this now so you know, okay? If you haven't heard this unit before, it's called an electron volt. Of course you have, because the hydrogen energy is minus 13.6 over n squared. Are you working electron volts before? Density functional theory, you must work in EVs, right? So room temperature is 1/40th of an EV. That's 0.025. 0.025 EVs. We're going to do this later in detail. 0.025 EVs. In order, you can see immediately, for example, hydrogen is 13.6 E. Well, to get it to the first excited state of hydrogen is about 13.6 minus 13.6 over 4 is minus 3.6. So it takes about 9 EVs. Think about what that is. That's thousands and thousands of Kelvin worth of energy to excite hydrogen. Okay, so 1 EV worth of energy is about 12,000 degrees. So you would need a reservoir, okay, the environment with a temperature of 12,000 degrees.
In Celsius. Celsius, right?
So no, Kelvin.
Okay.
Do you work in Kelvin?
Yeah.
Okay, Kelvin. Kelvin and Celsius, same thing. It's only an offset of a few hundred degrees, right? So 12,000 Celsius, 12,000 Kelvin, or either way. So in order to get 1 EV worth of energy to excite something with 1 EV, you need a lot of heat. Get further down, the electronic ones are crazy, all right? But then you have the vibratory ones. Those are on the order of room temperature. Those are on the order of room temperature. If it's a gas, they'll do this. But if they got nowhere else to go, here's the important point. If they got nowhere else to go, they'll just exchange energy with each other and they'll be an ideal gas for all intents and purposes. If you can rotate them, rotate this one comes along, this one's rotating, maybe this one rotates. Over the course of time and averaging, it's the same problem. The energy can't get out from a perfectly isolating piston. So even if they interact, it can't go anywhere. You reach thermal equilibrium no matter what. By the way, here's how you know that the scale of vibration is much, much smaller than the scale of electronic transitions and the scale of rotation. The reason you know that is your microwave oven and you. The reason you know that the scale of vibration is small is because if I put on infrared glasses, I can see you in the dark. That's infrared. That's infrared. What's happening? That's infrared. Okay. What's happening in your microwave is you're trying to get this to turn water. I think it's a vibrational mode of the water molecule. I'm no expert. I need engineers. Anybody know any engineers? Somebody tell me but I'll look it up. I'll look it up. But it's a vibrational mode and you need microwave energies. Okay. So maybe I have it backwards, but either way, the scale of the problem is different. The scale of the problem is very different. But if the energy can't get out, it doesn't matter. They'll equilibrate among each other. That's the beauty of thermodynamics and the idea of thermal equilibrium, which actually is related to maximum of something, and that maximum of something is entropy. Okay, maximum entropy is sort of equivalent, not sort of, is in general equivalent to thermodynamic equilibrium.
If I got it clear from your description,
Yeah.
the temperature change is coming from the molecules moving up and the piston heating.
The piston turning around faster than it comes out faster than it goes in, and higher kinetic energy means higher temperature. That's what temperature is, higher kinetic energy.
Then the piston goes.
If the piston goes up, you're giving it up. And it will continue to increase in temperature as the piston keeps coming down. Yeah.
Does this have dependence in direction of the piston? Like if the piston is, what if the piston is coming from
It doesn't make any difference because 1/6 of them is coming. 1/6 of here. Yeah, 1/6. Yeah. 1/6, 1/6, 1/6, 1/6.
Matter the direction.
Yeah. I was like, are the people in Australia upside down? No, they're just fine. All right, so that's the first law. The second law is something my chemical people know better than me. Maybe not, at least it's good. The second law states entropy of a system out of equilibrium will tend to increase. I'll write the word. This class is so much fun. This class is really fun when I have interested students. The entropy. Well, if nothing else, young people, you learned something today. Why does a gas heat up when you compress it? And it's a real lesson into asking yourself why, like a child. Somebody comes to you on the street and say, well, you're standing up here, a gas heats up because you compress it. And then some 12-year-old asks you why. Huh? I don't know. How you do? Entropy will increase. Let me write it the way I actually have it. The entropy of a system out of equilibrium will tend to increase. This is a good descriptor, but we need some quantitative thing. You all know entropy tends to increase. To get entropy to decrease requires some work. You can, of course, make the entropy decrease in one little location in the universe. You know how you know that? Because you have a refrigerator. You have a refrigerator. And inside your refrigerator, when you first plug it in and turn it on, it's warm in there. Then you suck out heat and the temperature goes down and the entropy inside the refrigerator increases. Does the entropy of the universe decrease? It does not. The decrease of entropy in the refrigerator is far, far, far overweighed, over whatever the word is, by the entropy you pump into the universe in the back end of the refrigerator as the waste heat is dissipated. All right. What does this imply? This implies you keep striving toward equilibrium, and once you get there, maximum entropy, I'll write this as max S, is equivalent to equilibrium. This is the guiding, as much as any principle in this course, maximum entropy, driving the system driving toward maximum entropy is the equivalent to equilibrium. Another statement of the second law that I'm not going to write down, you'll see it in the notes. I'm just going to say it because this is so obvious. I don't need to say it, write it down for you. Another way you can say the law of increase of entropy, the second law is that it's impossible for heat to flow from a cold body to a hot body on its own. That you probably have heard before in your class. The one thing that an example that when I discuss this is, oh, and let me just finish this. So another way to write that is ds is dq for any real process over the temperature of the reservoir is always greater than zero. Any heat you transfer over the temperature of the reservoir, the entropy is always greater than zero. And that's the general physics textbook. And also can found, as I say, a good summary of the second law that gets to the gist of the matter, which is the foundation of it, is in Wikipedia, but I can't provide the link. But now I can. I learned how to do it because the typesetting conflicts with LaTeX. Now I know how to do it. If you ever want, you use LaTeX? Have you ever heard of LaTeX? Do you know how to put a link in LaTeX? You use LaTeX?
No, I've not.
Okay. Oh, you got to learn how to use LaTeX.
Yeah.
You do this /href and you drop it in there.
Yeah.
Yeah. Did you know that already?
Yeah.
Well, how come you didn't tell me?
I was using it for my
Oh,
publication.
okay. You should have told me. You should have told me. You didn't know me. Still, he should have known. Don't you think he should have told me 2 weeks ago before he met me? Yeah, he's irresponsible. All right. But that's how you do. You knew it for real?
Yeah.
All right. I'm going to go back and find the link and put it in there, and I'll have an updated set of notes. There's one thing I wanted to say about this. Oh, interesting correlation to this, and it's a good example that I use all the time. Why can't you run an engine, say one of these cruise liners or whatever, right? Why can't you run an engine from the energy of the ocean? Just naturally use the energy of the ocean. This is because you can't take a colder body and pump heat and to run an engine. If you think about how much energy is in the ocean, it's a lot because there's kinetic energy of all that, right? So it should be simple. It should be very easy. There's a tremendous number of joules of kinetic energy in the water in the ocean, but you can't extract it and use it for work because you've got to go up the gradient, the heat gradient. So even though there's a tremendous amount of that made an impression on me for some reason. And I don't know, I guess not making less of an impression on you, but there's a tremendous amount of energy in the ocean, but you still have to run your generators at a hotter temperature than the ocean, and you can't get it to work that way. You just can't get heat to go up the cold to transfer its energy and make something hotter. All right. The third law says that the entropy of a system, S goes to zero as T goes to zero. This is also, I believe, called Nernst's law. N-E-R, Nernst's law. All right. You can never get to absolute zero. By the way, let me say something real quick. You'll see on the next page, figure 1, that's where I talked about. See, it's too small. So I'm going to go ahead and put the link in. Didn't print out the way I wanted it to. So I'm going to go ahead and put the link in, but that's the Wikipedia thing. It's essentially where I got this from. Yeah, it's Nernst's theorem. By the way, this was proposed in 1905. And of course, we all understand this. You have steam, you have a volume of steam, particle number N. That's a highly disordered thing. The things are moving all over the place. If you put it in ice, the volume is lower already just from condensation. And also the velocities are smaller. The kinetic energy is smaller. The internal energy is smaller. So the entropy is decreased. But then you take that water and you remove more heat and you get the molecules to click into space and into place. And now you have ice and that's the lowest. So there's an obvious intuitive understanding that the slower you go, the lower the entropy. Can you ever get to absolute zero? Highly unlikely. I don't think you can ever get to absolute zero. You have one issue also as well. You might think this may be a new idea to you, what I'm about to say. This might be a new idea for you, but there's no such thing. I don't care what it is. So you take some metal and you cool it down to as close to zero as you can get. One of the reasons you can never get it to zero, you're more familiar with this, is because of the Heisenberg uncertainty principle. Okay. It turns out you can never completely locate something infinite with exact precision and know its velocity. So the split second you can find something, it's automatically got 0-point energy. So there's always this vibrational thing that because of Heisenberg uncertainty principle says you can never set it equal to zero, because if you set its position perfectly equal to whatever, zero is a good number, and not moving, you would know nothing about its velocity. And yet you know it's there. It's not going 100 meters per second somewhere else. So it's impossible to reconcile Heisenberg's uncertainty principle with getting the temperature all the way to zero. I'm sure somebody watching this feed now will give me somebody in the middle of the nowhere in Brazil or something. Brazil's not the middle of nowhere, but somebody watching this video later, because I have people watch this overseas and ask me to solve problems for them, is going to say, "Oh, I know a technical way around that, yada yada yada." And the other ones I get from these videos is people who say, I've discovered a new source of energy that you can violate the second law of thermodynamics, the first law of thermodynamics. And if you sit there and carefully track down their argument, somewhere along the way, the number one, there's a battery or the equivalent of a battery. The other argument, at some point in the engine, at some point, this happened about 20 years ago to me, I couldn't find it. I couldn't find the problem when the guys, he said, I do this, I do this, I do this. I said, look at this thing. I'm looking at it. Right in one process, heat flows in that engine. I was telling you, heat flows from cold to hot, and I couldn't find it. And I looked. I said, okay, that's that. That's that. And I just wrote down all of it, and I got it. I got it. All right. So let's do. We always turn to the classical ideal gas to illustrate particular points. So this is. I should have written in this on page 4, the classical ideal gas. It's underlined. What I should have written there is classical ideal gas, Roman numeral 1, because we come back to the classical ideal gas again. All right. So this is classical ideal gas 1. The ideal gas law. None of you watch Big Brother, and I have nobody to gossip with about Big Brother. It's my favorite show. This is you watch Big Brother?
Which of the Big Brother?
You know what Big Brother is?
Yeah. Is it the one in Nigeria? Because we have Big Brother.
You have your own Big Brother?
Yeah. Big Brother Nigeria. Big Brother Nigeria.
Ms. A, do you watch Big Brother? He's gone. Is it 12 people, 15, 17 people in a house and then with cameras everywhere?
Yes, yes. But Big Brother Nigeria, like you said.
Yeah.
I'm so excited. You need to go on it. Victor, you need to be a house guest.
Yeah.
Would you do it?
The one in Nigeria might not be the same.
Okay. Okay. All right.
We also have Big Brother Africa.
Yeah.
So I've watched Big Brother Africa.
Okay, Big Brother Africa. How exciting. You don't know what Big Brother is.
What do you watch?
The one now. The one they have an eviction tonight. Big Brother America. Yeah, Big Brother 28. It's 28th season of Big Brother.
Oh.
I started watching it back, in 1997, 1998. So the classical ideal gas gives us a state law. You all seen this before. PV is nRT, where R is the gas law. And I think I have it written down for you. We know pressure. We know volume. We know temperature. N is the number of moles. And of course, to get the number of moles, we need Avogadro's number, and I'll write it down here. I believe it's 6.02. You would know this better than me. Times 10 to the power 23 particles per mole. That's how you get your units to work out with this kind of stuff. R is also equal to the number times KB, where KB is Boltzmann constant, and I don't think I wrote that down. This law was not, this turns out this law was not derived in the early part of the 18th century, actually middle 18th century. You guys might know the names Charles and Boyle and all these guys that established, okay, this is how the pressure relates to the temperature. This is how the pressure relates to the volume. This is at fixed temperature. But this is how it all came together in the middle of the 19th century. We can derive this from quantum mechanics in the middle of the 20th to 21st century, though. So, all right. So what are the assumptions we adopt to do this? So what are the assumptions underlying the ideal gas? They're the obvious ones, but it's a law that I could get fined by the International Congress of Physics if I don't tell you exactly the assumptions that go into the ideal gas. Of course, I'm making that up. There's no such thing, but I feel we should say them at least once. Assumption 1 or assumption A is what I have here. The gas consists of small particles. And just to put a scale this, we'll come back to this, okay? Their size, there's corrections you can make, by the way, to the ideal gas law. Their size is such that the number of particles you have times their volume is much less than the volume of the container. So that's the ideal gas, all right? Another way to say that is the average distance between the particles, call that D, is much less than their atomic radius. I'll call that R. So let's take a look at this, because one of the things the students who have had this class from me before will tell you that I spend quite a bit of time working out very simple things, high school algebra, junior high school algebra, to understand the physics. The example, or the question I just asked you about why does a gas heat up when it's compressed by a piston in a container requires no math to understand, but you now understand the physics and the scale. This is going 1/6 up, 1/6 down. Big mass coming down on small mass speeds it up very easily. All right. So let's talk about 1 mole of a gas in a piston. This number might surprise you when we're done. So we have N of the gas, N of the number. We'll take argon. Okay. Take argon. We'll have 10 to the power 23 particles in here. We'll make this piston 1 centimeter. Actually, I'm not going to make it. I'm not going to make it. That takes too much time. I'm going to make it a box so I can get that way I don't have to calculate pi r squared to get the volume. You see the point there? That's too much trouble. 1 centimeter by 1 centimeter by 1 centimeter. So it's a box this big. Okay. We're going to put argon or neon or something in the box. In this class, I don't need to know exactly how big it is. I don't need to know that. What I will tell you, if you don't know that, is the hydrogen atom floating around by itself with a proton and electron, more or less, the distance across is about 1 angstrom. You might, if you've taken quantum mechanics, you know its Bohr radius is about 1 angstrom, right? Across. So we'll say that argon is considerably bigger because there's a lot of electrons, or neon. One of the interesting things, though, it's not much bigger. It's not much bigger because what happens with argon and stuff like that is it's got a huge positive core in the middle, so these electrons really come in tight, right? So we'll say that it's 10 times bigger. We'll say that the diameter, the radius of argon, we'll say argon is 10 angstrom, which is 1 nanometer. Actually, yeah, it's 1 nanometer. That's a typical atomic or molecular size. So if I want to know what fraction I have of a 1 centimeter container, the volume of the atoms total would be number of the argon atoms I have times the volume of each one, which is pi r of the angstrom squared. The volume of the box or the container is 10 to the minus 6 meters cubed. Why is it 10 to the minus 6 meters cubed? Because 1 centimeter is 10 to the minus 2, isn't it? 10 to the minus 2 times 10 to the minus 2 times 10 to the minus 2 is 10 to the minus 6. So the fraction you occupy will be 10 to the power 23 times pi will take to be 3. Is that me or you? Times 3 times, we don't need the 5, but we'll put it anywhere. 5 times 10 to the minus 10. And that quantity is squared. And on the bottom, I have 10 to the minus 6. Have I got that right? No, that's, why did I say pi r squared? It's our pi r cubed, for God's sakes. You guys all knew this. Pi r cubed. It's actually 4/3 pi r cubed, right? Because they're spheres. but we'll just call 4/3. We'll just call it 4. 4 pi over 3. We'll just take that as 4. We do these approximations all throughout this class. So this is 2 times 10 to, this is 20, that's 10 to the 1. That's 10 to the power 24 times 10 to the minus 30. And you see an interesting thing happen pretty quickly here on the bottom. 10 to the minus 6. So they occupy, just look at this thing over here. They occupy double the amount, it seems, but obviously that's not what's happening. Obviously, you don't see what it is that's an overestimate for the size of argon by quite a bit. Okay. Nothing funny happens to a gas inside of a cube. So they're in there packed pretty tight, but there's nothing funny about it. But the reason I wrote this down is to illustrate that yes, this is the assumption we use. But one of the more interesting things is the corrections that have to be made because of the finite volume of the particles. I believe that correction is called the van der Waals equation, where they actually correct for the finite size of the particles, and it's just kind of an interesting thing. Part B here is the average number of particles, or the number of particles. The number of particles, I'll call that NP, is so large a statistical treatment is appropriate. I wrote that right on the damn line. Okay. And that is a pretty obvious one as well. This assumption is sometimes referred to as NP goes to infinity. This is known as the thermodynamic limit. You're going to hear me say that words a lot. So what it means is in the limit of an infinite number of particles. Okay, so I'm going to say that a lot. Part C, rapidly moving particles collide amongst themselves on the wall of the containers. The collisions of the particles are elastic. This comes back to the question you asked me, exciting the internal modes. Just complicates the problem. People have published papers and there's books on corrections to this, but for us at this level, he's got to worry about it more than you do. Well, I don't know, actually. I don't know. I'm starting to read up on density functional theory. So I can put a couple of lectures in on density functional theory. And I'm also reading up on the thermodynamics of the universe. You know what you're going to at some point calculate is the number of photons in the universe. You can calculate that. Well, obviously not exactly, but in principle you can. Collisions are elastic. In fact, they're not just elastic, they're perfectly elastic. Okay. D, the interactions are strictly binary and uncorrelated. And I'll just say this, the interactions are all two-body. There are no three-body or other complicating factors. Three-body interaction is one where the interaction depends on, in a complicated way, on R1, R2, and R3. So you can't just separate it as R1, R2 interaction, plus R1 plus R3 interaction, plus R2 plus R3 interaction. It depends on R1, R2, R3 intertwined in the coordinate space representation of the potential, all right? So they exert no forces on each other. So F12 is equal to F21, and that's it. Another way to say that is Newton's third law holds. Ask my chemical engineer this question. If you jump off a tree, does the earth come up to meet you?
If
You jump off a tree, does the earth come up to meet you?
Nope.
Not practically, but does it in principle? If you jumped off a smaller planet, instead of if you jumped off an asteroid, If you're on a tree in an asteroid, does the asteroid come up to meet you?
I go to meet it.
Newton's third law, yeah, but the asteroid comes up to meet you too. Newton's third law says what? Gravity of the asteroid, small little rock of an asteroid, right? A little tiny asteroid. What does it do to you? Pull you down. Newton's third law says, what do you do to it? Pull you up. Action reaction. Yeah, yeah. The reason the Earth is, 10 to the power 27 kilograms and you're 10 to the power 2 kilograms. So the Earth doesn't come up, in principle, you know. But if you were on, did you ever see the movie Armageddon? Armageddon, where they send a group of oil riggers. They send a group of astronauts, oil riggers, to blow up an asteroid in outer space. You never saw Armageddon? Ben Affleck, you know the actor Ben Affleck? Do you mean anything to you? Bruce Willis? No,
Bruce, yeah.
Bruce Willis is in it. Okay. So they go to this asteroid that's, I don't know, the size of, I don't know, Tallahassee or whatever. And they're all running around and the cars are hitting bumps and they're going up there, coming back down. If they're on that asteroid and they hit a bump, the car would do this and then do this. And then if they put dust up, what would the dust do? The dust would go up. In fact, the dust would go up quick, but what would it do? Take forever to come back down. Yeah, I worked out the gravity given the parameter. One time I worked out what the gravity was. It was like 1/10 of, whatever. First grade. But it's, so in principle, yeah, that's Newton's third law. All right. So let's do some kinetic theory. Okay, so let's see if we can somehow manage to work out the ideal gas law, or some of it. I mean, this is what they did in the 1800s, 1900s. No, 1800s, 1800s. All right. So we're gonna have a wall, and we're gonna put it on the YZ plane. So here's X, and this is YZ plane right here, YZ plane. So we have a molecule mass M and velocity V, and we'll just have Vx here. And you have Vx initial, and he's going to come in, and he's going to collide with that wall and turn around. So the change in momentum, which physicists call the impulse, I don't know if you've used that, if you call it that, change in momentum is impulse. No? Okay. See, this is why I'm going to go, every once in a while, please understand that I don't mean, I just don't know what you know. So I'm going to, like this vocabulary, you obviously know what the change in momentum is,
Yeah.
but there's words we use that you guys don't use, right? So delta P is P final minus P initial. So this will be M. If it recoils, this is minus V. This collision is elastic, and you consider the wall to be infinitely hard and infinitely big. Another way to say it is the mass of the wall, capital M, is much bigger than the mass of the particle. No problem. So it collides elastically, and this is M Vx initial minus M Vx initial. It's not zero because the directions change. When did you take general physics?
Undergraduate. About 7 years ago.
Okay, so I'm really going to fill in details. Please don't be insulted if you don't know them.
No problem.
Okay. So this is minus 2 M Vxi. Okay. The only ones that make it to the wall in some time t are the ones in this column. Now, listen up. I know they're moving all over, but we're only looking at the ones in the X direction right now. We have to go back and fix that up. But for now, just make the thing as simple as possible. This is a distance. I use the symbol little l. I wish I'd used big L, but I use little l. The only ones that can make it in there are the ones make it to the wall, are in a length L is Vxi. I should use capital V because then I could use a larger subscript. Delta T. So you have to be fast enough to make it there. So that's the number. The only ones that hit over some time t. If you're not moving fast enough, you don't make it. So the number, total number that hit, let's go back and look at what that total number that hit is, a number of that species Ni per unit volume times Vxi times delta T times A. Let's check our units. Ni is the number in that with Vxi. V is the volume. Let's put some hats on it there so we see it's the volume. Yeah, maybe that's why I didn't use capital V, because I use capital V for the volume. All right. And we take one line to get the impulse. This is why I wanted to make sure you knew what the impulse was. Total impulse, change in momentum. All right. So the total change in momentum J is double. We've already seen that. Is twice because of this 2. 2 Ni over V M V Xi squared times delta T times A. You can go back and fix all that stuff in there. The pressure is the force per unit area. And at this point, we can almost stop, but I want to keep going a little bit. So force per unit area, delta T. Simplify that. The details are less important than where we're going, but it's kind of nice to see it derived once in your life. This is less, actually, to my mind, those steps is less important than this step, which is the pressure is 1/2. This is PI. 1/2 the sum of all the particles. Why 1/2? Why 1/2? We just talked about this a minute ago. Because of the ones that are moving with speed V, what fraction of them are moving that way? 1/2. Before we were talking about 1/6, 1/6, 1/6, but we're only talking about in the one direction. And then we'll extend this. Real quick check. Is there anything special about the X direction? No. Is there anything special about the Y direction? Nope. Because we got walls everywhere, right? So when we want to do the pressure, we're only doing it along X, but everything we do for X will also be true about which other directions? Y and Z. So keep that in mind.
The 1/2 is like an average,
Yeah. Yeah. The 1/2 is as averaging over the ones, or really just cutting the other ones that are going to the left. If we have speed Vxi, right? So if this one's going 10 meters per second, somewhere in there's another one going 10 meters per second. That one doesn't hit the wall. That hits the other wall, but only hit this wall. So we're looking at this one wall. You're going to have to add them all up at the end of the calculation, right? So this is all of these. That cancels this 2 that I have here. And I will have M over V sum over Ni Vxi squared. And if you look at the next page, I actually don't need to do this. I know what the answer is, but I want to stay in line. So this last thing up to here, up to a normalization, is the point I want to make. When you add up the number of a quantity, why do I went through this entire derivation actually to get to this because I want to introduce an idea. When you have the number of something up to a normalization again, when you have the number of something times the quantity, 1 over n, and you have the number of something n of I and the quantity, I'll call it x of I. This is the average value of a quantity. This is the average value, all right? And I want to do a quick example with dice, even though I do this later, but I want to just show you what that's called. If you haven't seen that before, that's called the expectation value. That's the average value. So if you have a die and you throw it, how many ways can a die come out? 2 die. 6. You guys know what I'm talking about? You ever play Monopoly or something like that? So this has 6, this has 6, right? So the total number of possibilities are 36. We agree? So n is equal to 36. So for die, if I want to know what the average value of a roll of 2 die is, this is 1 over 36. And the sum. How many ways can I make a 2? One way. Dot, dot. And X is the roll of the die. How many ways can I make a 3? 2, 1 or 1, 2? 2 ways. How many ways can I make a 4? 3, 1, 1, 3, 2, 2. 2, 2. You say, what about 2, 2? No, you don't. It's just 2, 2. All right. So there's 3 ways to make a 4. How many ways to make a 5? 4 ways, right? Or 5. Yeah, 4 ways to make a 5. 4, 1, 1, 4, 3, 2, 2, 3. How many ways to make a 6? You see how it climbs up? 6 ways to make a 6. 3, 3, 2, 4, 4, 1, 1, 5. How many ways to make a 7? 6 ways to make a 7, and so on until you get to back to 12. And how many ways are there to make a 12? 1, 6, 6. If you were to add all these up, you would get 1 over 36. 1 plus 6 plus 12 plus 20 plus 30 plus 42. And all the way, you would get that number to be 252. And 36 in the denominator with 252 in the numerator gives me the average number of the roll of the dice to be equal to 7. Which is, by the way, why Las Vegas? Gambling. You ever heard of Las Vegas? Big city in the desert in Nevada. That's where you gamble.
Oh.
In the casinos, big casinos, right? So if you go to Las Vegas and you throw 2 die, you come out and you throw a 6. 4, 2, 2, 4, 3, 3. It doesn't matter. Throw a 6. To win, this is how it was in the old days when my father did this for a living. To win, you have to throw a 6 again. Okay? Before you can keep throwing, but you have to throw a 6 again before you hit what number? 7. What's the most probable number? 7. There's more ways to make a 7 than any other number, right? Look at it. That's why Las Vegas picks 7 as the loser. They take your money if you throw what's called snake eyes, which is 2 or a 7. So they got you. They got you. The odds of you winning, gambling is all about averaging, right? Gambling is all about averaging, and they know the number to pick for you to lose. That is why if you go to Las Vegas in the desert, they are constantly building bigger and newer casinos because people are constantly losing money. You cannot beat the house. It's called the house. The casino is called the house. So you learn a lot of physics, hopefully for me, but you also learn a little bit about how we do things here. America has developed very efficient systems for taking your money. One of them is Las Vegas. The other one is Disney World. Disney World is excellent at taking your money. Have you been? Orlando?
Yeah.
Yeah, Orlando's excellent at taking your money. The Disney World, no institution in America is better at taking your money and keeping a smile on your face than Disney. When you go to Vegas and you lose, you cry. When you go to Disney and you're losing all that money, you still smile because you're having a great time. All right, so that will eventually, we'll pick up from here next week. I'm going to put a couple of things up on Canvas, a couple of homeworks, and maybe the notes up on Canvas, so keep an eye out for that. We are still about a week away from giving you homework. So this is kind of the dead time that we're just talking physics and establishing, but the homework will be coming, okay? All right, we'll stop here. I'm excited to have a new student. She's probably thinking, why did I come here? Why did I join this?
And then, sir, had a good time, sir.
Did you?
Yeah.
And did you ever watch Big Brother?
No, not Big Brother America. No.
Not Big Brother. Oh, no. We have to start. There's still 11 people in the house. There's a big eviction vote tonight.
Oh, really? Okay.
Yeah. Yeah. Oh, yeah. I watch it. My daughter and I watch it.
Oh, that's nice.
I want to ask a question from the zeroth law.
Yeah.
So, say from the zeroth law, it says there exists a scalar quantity such that if two systems A and B are placed in contact,
Yeah.
they reach a common temperature.
Yes. That scalar quantity is the temperature.
Is there a possibility where three systems are placed?
Yeah, that's another way to write that is the extension of that. That's a good question. That's an excellent question. The extension of that, and you'll see it formulated this way. if temperature of A is equal to temperature of B, then temperature and B is put in contact with C, then temperature of A is equal to temperature of C. You also see it written that way too. Yeah. So the transitive property also holds.
Okay.
Yeah,
So I
yeah.
was thinking that the zeroth law only holds for just two systems.
And how it holds for as many as you want. In fact, it helps establish that transitive property.